Welcome back to the deep dive. Every time we look up at the night sky, we are overwhelmed by the sheer, almost impossible scale of the universe. Billions upon billions of stars.
It's truly
And
mind-boggling.
it makes the assumption that life is common seem, well, entirely rational. But today, we're taking those billions of stars and the planets that might orbit them and running them through the most rigorous, unforgiving checklist ever devised.
That's right. Our source material today, drawn heavily from the foundational work of Yusuf Shklovsky in his seminal book, Universe, Life, Mind, doesn't really indulge in broad, speculative possibilities. It's not about what could be.
Uh-huh.
It presents a scientific, step-by-step filtration process. We are moving beyond the question of, is life possible, and instead asking, what astronomical conditions are absolutely non-negotiable for complex, intelligent life to emerge, evolve, and thrive over billions of years?
This is essentially our mission, then, to find the cosmic needle in the galactic haystack by understanding all the ways the cosmos tries to kill off life before it even gets started.
A good way to put it.
We're going to be unpacking the habitable zone constraints, the precise physics of atmospheric retention, the necessary constraints on stellar age and metallicity.
And even delving into the surprising orbital mechanics that might or might not allow life in a binary star system.
It's a huge topic.
It is, and we have to begin with the most fundamental requirements: time, stability, and placement. I mean, if a potential system fails any one of these early astronomical tests, the entire enterprise is moot.
Right. You don't even get to the chemistry phase.
Exactly. We need to define the cosmic rules that govern the emergence of complex chemistry and ultimately sustained biological evolution.
Okay, let's unpack this by starting with the most basic necessity for complex organization.
Hmm?
Time. We aren't concerned with finding, say, a single-celled organism that popped up and died after 5 million years.
No, not at all.
We are talking about the vast time interval required for evolution to run its full course, for simple life forms to diversify and eventually develop intelligence.
That's the critical distinction. Evolution is driven by mutation, environmental pressure, and natural selection. And these processes are inherently statistical and random.
It's a numbers game.
It's a massive numbers game. To realize the lawful development from lower forms of life to highly organized sentient beings, you require vast, almost incomprehensible temporal resources for those statistics to properly play out.
It's the sheer number of biological experiments that have to fail before one major success is achieved.
That's it, precisely. Millions, maybe billions of dead ends for every evolutionary leap forward.
And what's the only benchmark we have for how long that takes?
Earth. It's our only data point, our N of 1.
Right.
And the Earth benchmark suggests this evolutionary interval exceeds 3.5 billion years. That's based on the earliest fossil evidence of life all the way to the eventual rise of multicellular organisms and then, much later, intelligence.
So if we accept the Earth model as our minimum required timeline, we impose an immediate and massive constraint on our search.
Absolutely. So immediately, this 3.5 billion year requirement acts as our first astronomical filter, the star age requirement.
Which means highly organized life can only be expected on planets orbiting stars that are sufficiently old and, crucially, sufficiently long-lived.
And that allows us to begin filtering the stars by their spectral class. This is where we can make our first big cut.
Okay, so how does that work?
Well, hotter, more massive stars, those classified as OB and the early A and F types, they simply burn through their hydrogen fuel way too quickly.
Their main sequence lifespan is shorter than the evolutionary clock needs.
Much shorter. The analysis in the sources shows that stars must be later than spectral type F0 to offer the necessary billions of years for organized life to have even a chance to develop.
That eliminates the most massive, brightest, most visually stunning stars we see in the night sky.
All the big ones.
They're the astronomical equivalent of a Roman candle. Beautiful, but gone in a flash.
A perfect analogy. But the filter tightens further still. Shklovsky argues that planetary systems themselves are only likely to form around stars later than F5.
Okay, so we go from F0 to F5. That's a more restrictive cutoff.
It is, and this brings us to a slightly more contentious cutoff point.
Tell us more about that F5 boundary. The sources mentioned that this is based on arguments concerning stellar rotation and binary statistics that are often deemed unreliable or non-strict proof. So why do we still use it?
It's used as a practical, optimistic boundary because of observed correlations. You're right, the unreliable arguments largely stem from observations of stellar rotation and angular momentum.
So how fast the star is spinning?
Exactly. Stars earlier than F5, the hotter, bigger ones, tend to rotate extremely quickly. This rapid rotation is linked to strong magnetic fields, which may interfere with the formation and stability of a protoplanetary disk.
How so? What does the spinning actually do to the disk?
Well, there are a few theories. Faster rotation might cause the star to drag the inner part of the disk into it, just gobbling up the planet-forming material. Or it might induce such powerful solar winds early on that they strip away the lighter elements before terrestrial planets can properly coalesce.
So it's a messy, violent environment.
Very messy. The idea is that a slower rotating star provides a more quiescent, stable nursery for planets to form.
So if we adopt the F5 cutoff, we're essentially saying we need a star that's stable and long-lived, which gets us past F0, and ideally one that rotated slowly enough early on to allow a clean, stable planetary disk to form. And that gets us to F5.
That's the hypothesis. So being optimistic and setting our high end at F5 and our low end at K5, where the stars are still large enough and hot enough to maintain a viable, habitable zone, which we'll get to soon, we define our stellar Goldilocks window.
Main sequence stars falling between F5 and K5.
That's our sweet spot.
That's our physical boundary, but now we have to apply a crucial chemical filter, often termed metallicity. This takes us back to the star's birth environment.
This is a foundational constraint noted by E.A. Debye, among others. When an astrophysicist talks about metallicity, they mean the abundance of elements heavier than hydrogen and helium.
Oh, everything else, basically.
Basically, yes. Carbon, oxygen, iron, silicon. And why is this critical? Stars of the first generation, often referred to as population 2, or subdwarfs, formed when the universe was young and largely pristine.
Right after the Big Bang.
Their raw material was almost purely hydrogen and helium, lacking the necessary heavy elements to build anything solid.
So these first-generation stars are chemically sterile, at least in terms of forming planets like Earth.
Precisely. You can't build a house without bricks. Earth-type planets require vast quantities of iron, silicon, magnesium, and oxygen to build their cores, mantles, and crusts.
And those heavier elements, where do they come from?
They're forged deep inside massive stars and then dispersed only when those stars die violently as supernovae. The death of one generation of stars seeds the birth of the next.
So therefore, Earth-type planets cannot possibly coalesce around these metal-poor first-generation stars. We need second-generation or later stars.
Metal-rich stars, like our sun, that incorporated that recycled supernova material. This chemical constraint eliminates a massive, older population of stars across the galaxy.
So let's take stock. We have filtered by age, getting us to F0. We've filtered by the speculative F5 formation argument, and we've filtered by chemical composition. What's the numerical damage? What are we left with?
If we accept that optimistic F5 to K5 range, and we couple that with the metallicity requirement, we find that only about 1 to 2% of all stars in the galaxy are potentially habitable host candidates.
1 to 2%. That number, after hearing about billions of stars, feels devastatingly restrictive. It suggests that finding life is fundamentally rare.
Proportionally, it is extremely restrictive, no question. However, this is where the sheer mind-boggling scale of the cosmos intervenes to offer what the source material calls a comforting conclusion.
Okay.
We estimate the Milky Way contains roughly 150 billion stars.
Right. A number so big, it's hard to even imagine.
And even 1 to 2% of that immense number is still a massive statistical pool.
So after applying the age and chemistry filters, we are still left with potentially at least 1 billion stars that might host life-possible planetary systems.
1 billion at the low end, maybe more. The criteria are harsh, yes, but the raw number of opportunities ensures that rarity at the star level doesn't mean impossibility at the galaxy level.
That's the key takeaway from this first section, then. The statistical weight of the galaxy overcomes the low probability imposed by the age and metallicity criteria.
That's right. We have our list of candidate stars. Now, we must turn our attention to the immediate environment they create for any orbiting planets.
That brings us squarely to the Goldilocks zone, or the habitable zone. We established that life is complex, coordinated chemistry, and that requires complex molecular compounds.
Which in turn requires suitable conditions, primarily a liquid medium for chemical reactions to occur. For us, that's water.
Absolutely non-negotiable. Without a dense atmosphere and, crucially, a hydrosphere, a large, liquid water-enveloped complex chemistry just can't persist.
A world like the moon, utterly lacking these things, simply cannot host life regardless of its composition. It's a non-starter.
And the temperature constraints must be incredibly tight to allow for a liquid solvent like water to exist under stable pressure conditions. Life requires temperatures that are neither too high nor too low.
And crucially, minimal abrupt fluctuations over cosmic time. Stability is everything.
So the constraints are asymmetric. The source material emphasizes that the high temperature limit is considered more dangerous for life processes than the low limit. Why is that?
To understand why, you have to look at the fundamental chemistry of life. Biological molecules are large and complex, often built around these long carbon-carbon bonds.
The basis of organic chemistry.
Exactly. Extreme heat delivers energy that breaks these bonds. It denatures proteins. It destroys DNA. It literally shakes the molecules apart.
Like trying to build a delicate sandcastle in a hurricane.
A very hot hurricane. Look at Mercury. Its sun-facing side exceeds the melting point of lead. Life's foundation is chemically impossible under such heat.
So high temperatures chemically destroy the machinery. What about the cold end, like Uranus or Neptune, where surface temperatures hover around minus 200 degrees Celsius? That seems equally prohibitive.
It is prohibitive for active life, yes. But the key difference is that low temperatures halt biological activity without necessarily destroying the underlying machinery.
Ah, okay.
This is where the fascinating caveat of anabiosis comes in suspended animation. The simplest forms of life, like viruses and bacteria, can enter a state of deep dormancy near absolute zero.
They're inactive but preserved.
Their molecular structures are intact, so if a planet periodically freezes, life might pause and restart. But if a planet periodically boils, life is irrevocably destroyed. There's no coming back from that.
So that's why high temperatures are the harsher constraint on the emergence and maintenance of complex biological systems. The inner edge of the habitable zone is a hard wall.
It's a wall of fire. The outer edge is more of a deep freeze you might be able to recover from.
And the size and position of this HZ depend entirely on the star's power output, its luminosity.
Directly. Brighter, earlier spectral class stars have massive, distant habitable zones. But the low luminosity stars, the red dwarfs, M and late K class stars, present one of the biggest challenges to the universality of life.
There are a lot of them.
They constitute the vast majority of stars in the galaxy, something like 75%. Yet their HZ is geometrically restricted. Because they are so dim, the outer radius of their HZ can be smaller than the orbit of our own planet Mercury.
That is an incredibly tight orbit. The probability of a planet forming precisely within such a narrow band must be, well, statistically low, as the sources suggest.
The geometric argument suggests low probability, but the dynamic argument is arguably worse.
How so?
When a planet orbits that close to its star, it quickly becomes tidally locked, just as our moon is locked to Earth.
So one side of the planet perpetually faces the star, roasting, while the other side is locked in eternal night, freezing.
Exactly. This creates massive temperature differentials and complex atmospheric circulation issues that challenge stability. You might get a thick enough atmosphere to circulate the heat, but it's a huge challenge.
Here's where it gets really interesting, though. Even if a planet does form there and somehow develops a mechanism to circulate heat, there's a compounding lethal radiation problem, specifically mentioned in the source material's footnote regarding UV SETI stars.
Yes, the activity caveat. This may be the real killer for red dwarf habitability. The vast majority of these low-mass stars are known as UV SETI-type stars, famous for being highly magnetically active.
They don't radiate consistently?
Not at all. They erupt in violent flares. These flares generate intense bursts of hard radiation, especially X-rays and high-energy ultraviolet light.
And why is that hard radiation so lethal? Is it just the intensity?
It's the energy level. This intense hard radiation is highly efficient at atmospheric stripping. It can ionize the upper layers of a closely orbiting planet's atmosphere and accelerate the process of dissipation.
It literally blows the atmosphere into space.
Bit by bit, flare by flare, and even if life managed to start on the surface, constant sterilization events from these flares, coupled with the erosion of the protective atmosphere, likely excludes the possibility of life development in their vicinity over billions of years.
So the low probability of orbital location is compounded by the high probability of planetary sterilization and atmospheric loss. That's a triple threat for red dwarfs.
It is, and it significantly lowers our initial billion-star estimate. We must then apply one final filter to the stellar host itself: constancy.
So back to the star.
The central star's radiation must remain approximately constant, not just over a year or a century, but over the hundreds of millions to billions of years required for evolution.
Which immediately excludes the extensive class of variable stars.
Yes, any star whose luminosity changes greatly or periodically, like Cepheids or Mira variables, would doom its orbiting planets to repeated catastrophic climate swings.
Oscillating between runaway greenhouse conditions and global ice ages.
Over and over. It's impossible for life to adapt to that level of instability.
What's fascinating here, and what gives us hope, is the observation that the vast majority of main sequence stars, especially those near solar mass, radiate with astonishing constancy.
That consistency is derived from the physics of stellar fusion. It's a beautiful balance. Once a star settles onto the main sequence, the pressure created by outward radiation perfectly balances the inward force of gravity.
Hydrostatic equilibrium.
Exactly. And that equilibrium is extremely stable, so the energy output remains remarkably steady for billions of years. Our sun is the prime example.
And we have evidence for that in Earth's history.
We do. Geological and paleontological data confirms its luminosity has remained constant within a few tens of % over the last several billion years. This is a property that thankfully is satisfied broadly across our remaining F5K5 candidates.
So we have a relatively short list of stable, medium mass, metal-rich stars, and we now know where their habitable zones are. But wait, we said earlier that about half the stars out there aren't single. They have partners.
Right.
This brings orbital chaos into the mix.
This is where the physics moves from relatively simple elliptical paths to something far more complex. About half of all stellar systems are multiple systems. Binaries, triples, or even higher orders.
Which is more common than I think most people realize.
Oh, absolutely. Single stars like our sun are not the norm. And for a planet orbiting within the gravitational influence of two or more massive bodies, its path is defined by the restricted three-body problem.
Which is another way of saying the orbit is not a nice, predictable, closed curve. It's complex, perturbed, and often chaotic.
Precisely. The initial pessimistic view was that this complex orbit would be fatal. The planet would swing wildly, experiencing gravitational tugs that move it close to one star and then far away from the other.
Leading to temperature fluctuations or thermal flux variability. That would be absolutely unacceptable for life stability.
A 10% temperature swing can trigger a runaway greenhouse effect. A 50% swing is instant sterilization.
But the sources introduce a major breakthrough from over 30 years ago by Su Shuang. What was the key physical insight that allowed us to put life back on the table for some binary systems?
The insight was that the chaos is bounded. It's not completely random. Specific, predictable periodic orbits exist where the combined gravitational and thermal inputs from the multiple stars balance out.
So there are islands of stability in the chaos.
Exactly. But there's a huge necessary precondition. The relative stellar orbits must be close to circular. If that condition is met, then the planet's surface temperature can, in theory, remain within life-compatible limits.
That suggests that the planet must be either very, very close to one star or very, very far away from both. Let's try to visualize these stable regions using the concept of Lagrange points L1 and L2.
Yes, the Lagrange points act as gravitational boundaries. They're points of equilibrium. L1 and L2 points define regions of critical gravitational stability. Life-supporting orbits fall into two categories relative to the stellar separation distance.
Let's start with type 1. The planets that orbit both stars at once. The circumbinary configuration, a real-life Tatooine.
The Tatooine orbit. If the two stars are close together, their combined gravitational field acts almost like a single star from a distance. Suitable orbits exist outside the critical surface, passing through L2, the boundary on the far side of the system.
The planetary orbit must be wide enough to encompass both stars comfortably.
Right. For equal mass components, the stability requires the distance between the stars, which we call a dollar, to be relatively small. All must be less than 0.4 times the square root of the luminosity. If the planet gets too close to the binary pair, the gravitational tugs become disruptive and tear the orbit apart.
So for type 1, the planet sits far outside the binary pair. What about the type 2 scenario, the circumindividual configuration, where the planet orbits just one star?
That requires the stellar components to be far apart, creating two distinct, stable, habitable zones, one around each star.
Like two separate solar systems that just happen to be gravitationally bound.
A good way to think of it. The suitable orbits must exist inside the critical surface passing through L1. That's the gravitational saddle point between the two stars. The planet must remain tightly bound to its host star.
And the math for that.
This requires a dollar to be greater than 2 times the square root of dollars.
And as the stars get even further apart, We could ignore the companion entirely.
Exactly. If the separation distance exceeds 13 times the square root of dollars, the companion is so remote that we can treat the planet's host star as a single, isolated star for all practical HZ calculations. Its gravitational tug is negligible.
Okay, so we have two life rafts. Either the stars are very close, forcing the planet far out, or they're very far apart, allowing the planet to orbit closely around just one.
Yes.
But that mathematical definition means there must be a zone of exclusion right in the middle.
This is the critical finding, the exclusion zone. There is a specific band of intermediate distances, defined by 212 being greater than 8a, which is greater than $1.04, where life-bearing planets are excluded from the system entirely.
If the binary separation falls within this zone, the system is catastrophically unstable for habitable worlds.
Completely unstable.
Why is this intermediate zone so lethal? Conceptually, what's happening to a planet that tries to orbit there?
The planet experiences maximum instability. It's in the worst possible place. If it tries to orbit Type 1, circumbinary style, the companion star is too close and causes massive, non-periodic perturbations that throw the planet off course.
It could get ejected from the system entirely.
Ejected, or it could plunge into one of the stars. If it tries to orbit Type 2 around just one star, the companion is close enough to deliver enormous destabilizing gravitational kicks every time it passes.
So it's constantly being tugged out of its nice circular orbit.
Violently. These kicks stretch the planet's orbit, creating rapid, devastating swings in thermal flux, the exact opposite of the constancy required for life.
So the overall conclusion is that life is possible in multiple systems, provided they satisfy those strict, narrow separation conditions, and crucially, provided the stellar orbits themselves are nearly circular.
Yes, the probability is certainly higher around single stars, but the key takeaway for our large-scale statistical estimate is that accounting for binary systems doesn't fundamentally reduce the order of magnitude of potentially inhabited stars in the galaxy.
We subtract a large number of systems, but we are still left with billions of possibilities.
That's the idea. The numbers are crude, but the order of magnitude holds.
Now for the ultimate local test case, one of the closest neighbors to us, Alpha Centauri. It's a compelling triple system, incredibly close, but does it pass the binary filter?
Alpha Centauri A and B have a semi-major axis of 23.4 astronomical units. That large distance is generally favorable for circum-individual HZs. It falls into that Type 2 far-apart category.
So far, so good.
The gravitational calculations suggest stability should be possible around A or B individually.
But the massive caveat here is the high eccentricity.
Exactly. Their orbital eccentricity is 0.52. This orbit is highly elliptical, far from circular.
So they swing in close and then far away from each other.
Dramatically so. And remember, Xu Huang's breakthrough depended on the stars having nearly circular orbits. High eccentricity means that the distance between A and B changes over time. This variation causes the gravitational perturbations on any orbiting planet to also vary, potentially moving the planetary system in and out of the stable zone.
Creating unacceptable thermal flux variations. So even though the stars are usually far apart, that elliptical swing could periodically destabilize or cook a planet.
It requires deep, special consideration. The simple model breaks down. And as a final hurdle for Alpha Centauri, there's that age issue again. The system may be relatively young and not yet settled securely on the main sequence.
So the constancy of radiation itself is questionable, regardless of orbital stability.
Right. Alpha Centauri remains an exciting but deeply challenging candidate.
We spend a great deal of time filtering stars, but now we shift focus entirely to the planet itself. The star can be perfect, the orbit can be stable, but if the planet can't hold on to an atmosphere for 3.5 billion years, it's game over.
This moves us into the realm of planetary mass, gravitational physics, and atmospheric chemical composition. The beautiful complexity here is that these three factors are intimately interconnected. They define what you called the planetary shield.
Let's delve into atmospheric escape or dissipation. How does a planet lose its air over cosmological timescales?
The primary mechanism is known as thermal escape, or sometimes Jeans escape. It's based on kinetic theory.
Okay.
Gas atoms and molecules in the exosphere, the very top layer of the atmosphere where the gas density is low and collisions are rare, are constantly moving around at high speeds.
Bouncing around.
Exactly.
Yeah.
And if a particle gains enough kinetic energy to give it a speed exceeding the planet's escape velocity, it flies off into space and is lost forever.
Like tiny bullets firing off into the vacuum.
Precisely. And the speed of this loss depends Exponentially on several factors, notably the planet's mass, which determines its escape velocity, the temperature at the exosphere, which determines the average speed of the particles.
And crucially, the mass of the gas atom itself.
That's the big one. Lighter gases like hydrogen and helium have a much higher average speed at a given temperature. They're zippier, so they escape orders of magnitude faster than heavier elements like nitrogen or oxygen.
This mechanism immediately introduces the low mass limit. If the planet is too small, its gravity just isn't enough to hold anything but the heaviest gases.
If the mass is too low, the escape velocity is too small, and you lose the entire atmosphere relatively quickly, geologically speaking.
And we see examples in our own solar system.
We do. The Moon is 81 times less massive than Earth, with an escape velocity of only 2.4 kilometers per second. It has lost everything over cosmic history. Mercury is similar. The gravity is just too weak.
But Earth provides a startling, counterintuitive example of this physics in action, even with its substantial mass. The source mentioned hydrogen.
The math regarding hydrogen is genuinely startling. If we calculate the rate of thermal escape based on the high temperature of Earth's exosphere, which can be around 1500 Kelvin, the formula predicts that all the free hydrogen currently in Earth's atmosphere would dissipate into space in only a few years.
A few years. How is Earth not bone dry and airless then? What's going on?
It's because of continuous replenishment. That's a key part of our planetary system's stability. The hydrogen we lose is constantly being replaced.
Where does it come from?
Water vapor rises into the upper atmosphere, is dissociated into hydrogen and oxygen by solar UV radiation, a process called photodissociation, and the light hydrogen then escapes.
And this loss is balanced by what?
It's balanced by continuous geological cycles outgassing from volcanoes, and most importantly, the constant evaporation of the global ocean. This shows that the minimum planetary mass must be high enough to allow these replenishment cycles to operate effectively over billions of years.
So you need enough gravity to slow the loss to a manageable rate that can be replenished.
Exactly. The constraint dictates the minimum mass suitable for life must be around a few hundredths of Earth's mass.
So don't be too small. Now let's look at the other side of the curve, the high mass limit. If the planet is too massive, approaching the size of the gas giants, it runs into the opposite problem.
It keeps too much air.
Right.
If a planet is too large, say, tens of times Earth's mass, its gravitational field is so strong that it retains its primordial atmosphere. It simply cannot lose enough gas to change its composition. Its gravity is just too powerful.
What was that initial primordial atmosphere like back when the solar system was forming?
The initial condensation medium in the solar nebula was similar in composition to the stars themselves, overwhelmingly rich in hydrogen and helium, the two lightest elements.
So if a planet is massive enough to hold on to all of that, it develops an incredibly dense, reducing H-key atmosphere like Jupiter or Saturn.
Yes. And the sources point out that if these gas giants were only 5 to 10 times more massive than Jupiter, they would ignite deuterium fusion and essentially be massive brown dwarfs radiating substantial heat of their own.
And that composition leads directly back to the chemistry problem. Why is a hydrogen-rich atmosphere inherently detrimental to the formation of complex life as we know it?
This is where we examine academician V.G. Fizenkopf's argument. The chemical compounds resulting from a hydrogen-rich or reducing atmosphere ammonia, methane, highly reduced forms of carbon are considered poisonous gases.
Why poisonous?
Because they are biologically inert or actively destructive to the types of complex organic chemistry that led to terrestrial life. A reducing atmosphere lacks the free oxygen necessary for efficient oxidative metabolism and may prevent the complex polymerization required for biological molecules.
But the author notes that this view is debatable. Why is it debatable? Could primitive life arise in a hydrogen-rich environment?
It raises profound philosophical and chemical questions. Why is it debatable? First, you could have life that utilizes entirely different solvents, not water. Perhaps liquid methane or liquid ammonia, which would be stable under those conditions.
So non-water-based life.
Right. Second, life might not require oxygen at all. Early Earth life was anaerobic. It's only later that oxygen became critical. Third, the toxicity argument assumes the life form resembles Earth life. What if life utilized silicon chemistry or existed deep within the atmospheric layers where temperatures and pressures moderated the chemical interactions?
So we can't completely exclude large planets, but we must acknowledge that their environment makes terrestrial-style complex life highly improbable.
Exactly. The constraints stand for life as we know it. The mass must be manageable. So we have a huge yet bounded window for suitable planetary mass.
The lower boundary is a few hundredths of Earth's mass to prevent total escape.
And the upper boundary is maybe tens of times Earth's mass to avoid retaining that toxic primordial HE atmosphere.
That's a wide range, but it's defined by a deep interplay between gravitational physics and the necessary atmospheric chemistry required for complexity.
We have established 4 independent criteria: stellar age, stellar metallicity, orbital stability in the HZ, and the necessary planetary mass to hold a specific, non-primordial atmosphere.
A lot of hurdles.
A lot. And if these requirements were truly independent, the probability of finding a habitable world would be astronomically low. You'd be multiplying many tiny probabilities together.
But the key insight here is that the conditions for life are not independent. They must be linked by the process of planetary formation or cosmogony.
Yes. Consider the alternative. If you argued that Earth formed from matter with the exact same chemical composition as the Sun, overwhelmingly rich in hydrogen and helium, you run into an immediate, insurmountable problem.
The dissipation problem we just discussed.
Correct. No amount of subsequent thermal escape or dissipation could have sorted out that overwhelming primordial HE abundance over cosmic history. We couldn't have selectively lost enough HE to arrive at our nitrogen-oxygen-rich atmosphere.
The numbers just don't work.
They don't. Therefore, the implication is powerful. The original matter from which Earth and the other inner planets formed must have already been poor in hydrogen and helium.
Meaning the building blocks were primarily dust, silicates, and heavier molecular aggregates, the metals.
This is a crucial distinction tied directly to location and temperature gradients in the early solar nebula. Conditions close to the Sun in the inner solar system were hot.
So the light stuff boiled away.
It favored the volatilization and stripping of H and He due to intense stellar radiation and solar wind. It left behind the non-volatile HET-poor material to coalesce into terrestrial planets.
And further out.
Contrast that with the outer solar system, where lower temperatures allowed massive HE-poor gas condensations to persist, forming the gas giants.
What's fascinating here is how the sources call this a key insight into habitability, because it takes multiple low probabilities and shows they are systematically connected.
It is the ultimate reassurance for the prevalence of life. The circumstance that planets with atmospheres suitable for complex life-low HA rocky composition are naturally formed relatively close to the Sun, in the habitable zone, is not a coincidence.
It is a natural systematic consequence of the planet formation process itself.
It's built into the physics of how solar systems form.
So if a system forms planets at all, the planetary composition that we need for life tends to form precisely in the orbital region where the temperature is already right for liquid water. This increases the likelihood dramatically.
Precisely. Multiple requirements, orbital position in the HZ, suitable mass, and favorable atmospheric chemistry are fulfilled simultaneously by the cosmogony. This dramatically increases the estimated number of worlds where life can arise within a given system.
It pushes our overall statistical estimates back toward that billion-star range.
It does. That systematic connection is a huge boost. But we can't forget the ultimate requirement for complex life as we know it. The liquid water envelope, the hydrosphere.
The cradle of life.
Absolutely. Initial forms of life require a liquid solvent to facilitate those complex, coordinated chemical reactions. To form a robust, persistent hydrosphere, a substantial portion of the original hydrogen in the planet-forming material must combine with oxygen to form water.
And that water in liquid, solid, or vapor form must not dissipate over the eons.
And that brings us back full circle to that precarious mass balance we discussed in Section 4.
It all connects.
It adds a stringent combined condition on the planet's mass, its radius, and its orbital distance. You need enough gravity and warmth to hold the water vapor and prevent catastrophic loss, but not so much gravity that you turn into Jupiter and bury any potential water deep beneath a crushing H-feet blanket.
It's an incredibly fine line that the universe must walk.
It is. The fate of life hinges on the planet achieving this specific delicate equilibrium.
We've established all these cosmic rules, the filters of age, metallicity, stability, mass, and chemistry. Now, let's apply them to the only place we can truly measure, our own immediate cosmic backyard.
Let's bring it home.
We're going to use the 5-parsec model to see how rare our potential hosts actually are, even applying that optimistic F5K5 filter.
The visualization here is key. Imagine a sphere centered on our sun, spanning a radius of 5 parsecs. That's about 16.3 light years.
A pretty big bubble of space, but tiny on a galactic scale.
Exactly. If we were to construct a physical model of this volume, perhaps a plexiglass sphere, it would contain 53 distinct stars, counting the components of multiple systems like Alpha Centauri.
53 total opportunities for life. Let's start applying the stellar filters from Section 1. Who gets eliminated right away based on the age requirement?
We immediately exclude the bright, hot, early-class stars, those earlier than F5, because they burn too quickly for life's long evolutionary clock.
And this removes some incredibly famous, seemingly important stars.
The ones that often draw the eye. Sirius, the brightest star in our night sky, Procyon and Altair. They are young, bright, and transient. Their main sequence lives are just too short.
They are simply living too fast to support a 3.5 billion year evolutionary timeline. Now we tackle the vast majority of the remaining stars in the sphere.
The majority of the 53 stars are low-luminosity red dwarfs, M-class stars.
And we talked about the problems with those.
We did. And while we cannot definitively exclude them, some researchers hold out hope for extremely deep subsurface life. Their extremely tiny HZs, coupled with the high probability of sterilization via hard radiation from UV SETI-type flares, makes them unlikely candidates for complex life.
So for the purposes of finding robust, guaranteed habitability, we sideline them.
We do. Then we filter by the constraints of multiplicity. We exclude the volatile, unstable binaries in that exclusion zone we talked about, and systems like Alpha Centauri that have high eccentricity, which undermines the circular orbit assumption.
So we're really narrowing it down now.
We are focusing on stars that are metal-rich, stable, long-lived, and either single or in a very stable, well-separated binary that satisfies the circular orbit requirement. After systematically running the 53 stars through the complete checklist, excluding our sun from the candidate list, the reduction is dramatic.
So we exclude the early-class stars, we exclude the majority of the late-class dwarfs due to stability and HD issues, and we filter rigorously by multiplicity. How many are left standing?
Only 3 stars.
3.
Out of the original 53, only 3 meet the strict F5K5 solitary and stable criteria. These are the most robust initial contenders in our immediate neighborhood: Epsilon Eridani, Tau Ceti, and Gamma Indi.
Out of 53 stars, only 3 potentially meet the basic astronomical prerequisites for complex life. That is an incredibly powerful demonstration of how selective the universe is.
The rarity is immense, and it happens right on our doorstep.
It vividly shows that only a few % of stars might have habitable planets. The criteria we've discussed, age, metallicity, constant luminosity, HZ size, and orbital mechanics, have done the heavy lifting of reduction.
We often hear the phrase that the universe is teeming with life, but this kind of analysis shows that the prerequisites for complex life are extraordinarily specific.
This analysis, however, also provides the ultimate counterpoint to the disappointment of that 53-to-3 ratio.
That's the comforting conclusion once more. It shows that life isn't just about being in the right place, but being in the right place at the right time around the right kind of star, formed from the right kind of initial matter.
An incredible chain of requirements.
But because the galaxy contains 150 billion stars, if that 1 to 2% ratio holds true across the entire Milky Way, that initial billion-star estimate remains plausible. The universe is incredibly particular, but it provides incredible opportunities.
We've established a monumental list of constraints today. To summarize, conference life requires a star of the right age later than F0 or F5, that is metal-rich.
Yeah.
It requires that star to maintain astonishingly constant luminosity over billions of years. It requires an orbital configuration that avoids the gravitational chaos of the binary exclusion zone. And most critically, it requires a planet that sits within the HEZ.
And possesses the Goldilocks mass heavy enough to keep a protective HE-poor atmosphere, but light enough to avoid becoming a hydrogen gas giant.
What's fascinating here is that while these astronomical criteria are incredibly strict, leading to just a handful of candidates in our immediate vicinity, the sheer scale of the galaxy still supports that comforting conclusion.
Despite the low probability per star, there are potentially billions of worlds where life could arise, fulfilling that systematic link between planet formation and orbital location.
So what does this all mean for you, the listener, as you track the cumulative rarity? We established that the inner HE-poor planets naturally form in the AG due to the formation process.
They get the right starting materials in the right location. It's built in.
So if life absolutely requires a liquid water envelope, a massive stable hydrosphere, The ultimate question is no longer about the star or the orbit.
The final hidden hurdle in this cosmic lottery is the precise mass balance achieved during planetary accretion. How effective was the initial planetary material in trapping just enough hydrogen to combine with oxygen to form a massive ocean?
But not so much that the planet exceeded the mass limit and retained its primordial, poisonous He envelope.
That delicate balancing act, determined billions of years ago during the accretion phase, is the true cosmic lottery for the emergence of life as we understand it. That's the question we should all be pondering as we look up tonight.